Welcome to Probability and Statistics. This is our final lesson in this series. We have reached the end of Elementary Statistics, 4th edition by William Navidi. In this final lesson, we are going to be looking at Chapter 4 and parts of Chapter 13. And this whole lesson is all about linear regression, or finding a line of best fit to a set of data, using that line to model our data, to make predictions about values that we don't have within our data. And then we're going to finish up the lesson by looking at hypothesis tests or statistical significance tests for the slope of a regression line. So with that, let's go ahead and get going here. We're going to start with this idea of correlation. As we talk about linear regression, as we talk about finding a line of best fit, what we're really asking is, if I'm looking at two different variables, is there a correlation or a relationship between those two variables? So, for example, I might have a situation where as one variable is increasing, the other variable is also increasing. So I have something that maybe looks like this, where again, as we increase on the horizontal, the vertical is also increasing. We would say in this case that this is a positive, has a positive correlation. And in this case, we notice that data looks rather linear. It's kind of in a line. So I might say that this is a positive, or has a positive, linear correlation. On the other hand, I might have a situation where that data looks something like this, where as the horizontal value gets larger, the vertical value gets smaller. But in this case, the pattern is maybe more curved. And so in this case, I might say that it has a negative because it's going down, it's decreasing. It's a negative nonlinear correlation. And then, of course, you could have the situation where you just have a bunch of points and you're looking at that going, wow, there is like no correlation at all. I can't tell what's up or down if one is increasing while the other is decreasing. This just simply has no correlation at all. Okay, or so weak that we can't even discern it with the naked eye. So that's what we talk about, or what we mean when we talk about correlation. Are the two variables correlated or associated in some way? All right, well, let's talk about least squares lines then, this idea of a line of best fit, and then we're going to tie into that this idea of correlation coefficient. You can kind of predict what that might mean. So when we talk about least squares line, imagine, for example, I'll take an example from a previous lesson where we looked at, I think it was the weight of dolphins, and we looked at, I think it was maybe the standard deviation or mean of the dolphins. I can't remember what, but let's suppose that I want to look at the correlation, or I wonder if there's a correlation between length and weight of dolphins. So I go out into the ocean, I capture a bunch of dolphins, I measure them, I weigh them, I release them back into their natural habitat unharmed, and I get all of this data. So every time I've measured the dolphin, I get something that looks like that. And as I might expect, sure enough, as the dolphin gets longer, it also weighs more. And so in this case, we would say again that this is a positive, or has a positive linear correlation. But I want to know more than that. I want to know, I want to be able to predict, for example, what would the weight of a certain dolphin be if I knew its length that isn't in this data set. So I want to find a line in this case, because if I look at this data, it's linear, like we said. And so I want to find a line that I can use as a predictor, as a model for this data. So I could just kind of eyeball it and say, well, if I look at kind of where the center of that data is, maybe the center of that data is, I don't know, right about there. And that line looks pretty good. That's the line I'm going to use. And I could maybe just use some simple algebra to find the equation of that line and call it done. Least squares line, though, when we talk about a least squares line, this is a particular type of line of best fit that uses a method of trying to minimize what's called the residual of our data. Okay, so let me explain that. When I draw that line through our data, obviously most of the points are not on the line. Some are above, some are below. When I look at the vertical distance from the line to any one of those points, this is what we call a residual. It's the difference in the y value or the height value of those two positions, the point that's on the line to the point that's not on the line. So our predicted point on the line to our actual point not on the line. And a residual is equal to, in fact, let me label this. So this would be our predicted value that we would get from the line. This is our actual value that we got when we went out to the ocean and actually measured the dolphin. And the residual is always in this order, actual minus predicted. And the reason that order is important is because if I do in this case actual minus predicted, notice my actual is smaller than predicted. It's below predicted. So when I do actual minus predicted, I'm going to get a negative value. Negative tells me that the actual is below the predicted. If I pick a point above the line, let's say I pick this point up here, and I look at the vertical distance to the line, if I were to find that residual, that would be a positive residual because the actual is above or higher than the predicted. Okay, so that residual would be positive. So the sign of the residual tells you whether or not you're above or below the line, or conversely, if your predicted is above or below the actual. Okay, so let's get back to least squares line. A least squares line, let me write this out. A least squares line, and then I'll show you in the diagram or in the plot what I'm talking about. The least squares line minimizes the sum of the residuals squared. All right, so what does that mean? The least squares line minimizes the sum of the residuals squared. What that means is if I take a residual and I square it, I'm visually, geometrically, I am creating a square. When I take 3 and I square 3, I'm taking 3 times 3, I get 9. Geometrically, what I've done is I've created a 3 by 3 square whose area is 9. So when I square a residual, I can think of it visually in this plot as creating a square that has area. And if I take this residual and I square it, I've created a square that has area. And if I do that for all of the points, the idea then is if I add all of those areas together, that gives me a value, right? I've got the sum of those squares. Well, as I move that line around, imagine moving that line up or down or tilting it, it's going to change the residuals, how far those points are from the line, which is going to change the sizes of those squares. Some squares will get larger, some squares will get smaller. And as I move that line around, what I'm looking for then is the situation where the line creates the smallest sum of all of those squares. That gives us our least squares line. Thankfully, we don't have to, nor will we ever do this by hand, figuring this out, because you'd literally have to figure out what is the area of all those squares, add it together, move your line a little bit, recalculate all of the residuals, square them, add them together, and see if that got you a smaller value. That would be ridiculous. Okay, so it's actually quite an easy process mathematically. It really just uses matrices if you're familiar with matrices. But we're not going to worry about that. We're just going to know that that's kind of the behind the scenes how we find a least squares line. Okay, so we have our least squares line. And now we have also this thing called correlation coefficient. So let's talk about that. Correlation coefficient is what we call the R value. That is a C. I'm having a really hard time writing. I'm not sure why, but trying not to be too sloppy here. Okay, correlation coefficient, this is our R value. And basically what a correlation coefficient does is it tells us how well our line fits the data. All right, so it's how well our line fits the data. All right, fits the data. Okay. R is always between -1 and 1. Negative, positive, not good, not bad. It just simply refers to direction. So the sign refers to direction. And what I mean by that is that if you have a negative R value, you are going to have a negative correlation. You're going to have a situation where as the X increases, the Y decreases. If you have a positive R value, you have a positive correlation. Your data is going up or increasing. As X increases, your Y increases. So that's all the sign refers to. It's not good or bad. It's just telling you which direction your data is going in. Okay. So that's one thing you find out from the R is direction, up or down, increasing or decreasing. The second thing that we find out from R, though, is strength. Okay. So when we talk about strength, -1 would in essence be a perfect line. It means that your data is exactly linear. Okay. So we wouldn't say that though, because there's always maybe a little slight variation. So we would just say that this is like a very strong negative correlation. Okay. Again, negative in front of it means it's decreasing, but the fact that it has an absolute value of 1 tells us that it is a very, very strong, for all practical purposes, perfect line data. Something like, let's say like a -0.7, well, we'd say that that's strong, right? It's a strong negative correlation. We get down to about -0.5 and it's moderately strong, right? So we're using adjectives here to try to define how strong. And one of the frustrations for some people is that there's no like hard, fast rule. Like, what is a -0.43? Is that somewhat strong? Is it fairly strong? You just kind of go with it, okay? But there are some guidelines, right? So that's why I'm doing this, because it kind of helps to get a sense of where things kind of start to tip and change. -0.3, you might say that that's somewhat strong, somewhat weak even. I might even say somewhat weak on this one, actually. I'm going to say somewhat weak. Negative. Okay, and I'll add negative up here because we always want to talk about two things with the R value. You always want to talk about strength. You always want to talk about direction. Okay, and then 0 would just mean that there's no correlation. All right. Now, as we continue positive, then if I think of like 0.3, positive 0.3. It's the same as the above, right? So 0.3, 0.5, 0.7, and 1. I'm just going to write same as above, but positive, right? So a 0.7 would be a strong positive correlation. A 0.3 would be a somewhat weak positive correlation. All right. So that's the idea behind R. R is going to tell you direction, positive or negative, based on its sign, and how strong it is based on its value between -1 and 1. One thing I want to just point out here is, and you will see this in media all the time. I shouldn't say all the time, as I make a very a bad statement there. But correlation does not equal causation. So be careful when you are reporting your own data. Be careful when you are looking at other people's data, whether it's in an article or just whatever it is. Just because there is correlation between data, it does not mean that one of those is causing the other to change. Okay, so go back to my dolphin example. Right? Where is my dolphin example? Where's my dolphin? There's my dolphin example. Just because length and weight are correlated. As a dolphin gets longer, it weighs more. It doesn't necessarily mean that the length is causing the greater weight. Now, again, okay, probably, right? Probably, and we could prove that, but it could be something else. Maybe as a dolphin gets longer, its cartilage turns into iron, which makes it super heavy. Now I'm being ridiculous, but I'm being ridiculous for a point, right? It's not the actual length that's causing it to be heavier. It's the iron that its cartilage is turning into that's really causing the weight difference. Okay. So again, being facetious, being extreme, but to make the point that we want to be careful that we don't assign causation simply because we see correlation. All right. So let's talk then about how do we find this least squares line. So I've got my data And I want to, I've got a scatter plot, and I want to know, how do I find the line that actually fits this data? And so what we're going to do is we're going to actually use technology for this, because again, this is not something there are ways to do this by hand. And I mentioned one of them is just to eyeball a line that goes through your data and pick a couple points and algebraically find the equation, if you remember that from your ninth grade algebra class. There is another way called the median line that you could do by hand, but at least squares, generally speaking, you would use technology to do this. And so that's what I'm going to do for this as well. So in our example, it says the table shows the winning times for the 100-meter run for various Olympic Games from 1928 to 1988. So we've got a table here. We've got not necessarily every Olympic Games, although it looks like we've got most of them. Actually, maybe we do have all of them. And then we've got the winning times for the 100-meter run for each of those Olympic Games. Okay, so that's the chart. And we are simply going to find the least squares regression line and the correlation coefficient for this data. Okay, so like I said, what we are going to do is we are going to use Excel for this. And I've already got my Excel table pre-populated with the data. We've got our year in column A. We've got our winning time in column B. All right, so there are two different ways that we can do this in Excel, and I'm going to show both ways just so you can see that. The first way is probably the easier way and provides a really nice visual as well. The second way is not difficult, but it just gives a bunch of data that may not be necessary, although we are going to use that second method when we get into the latter part of the lesson. So one of the ways to do this is simply to highlight your data. So if I just highlight all of this, I think I've got a just little Olympic time up at the top there, but I'm just concerned about the second part of this, right? So we highlighted this. You don't even have to highlight year and winning time, but if you do, it's going to add those as labels to your scatter plot. We're going to go up to the top and we're going to find the data tab, or excuse me, the insert tab. I'm getting ahead of myself. We're going to do the insert tab, and we want to insert a chart. So in the middle of the screen here at the top, there's all these different charts. Excel can do dozens and dozens of different types of charts. You could do recommended charts. It will recommend what it thinks is the best kind of chart for the data. But this isn't what I want. None of these are what I want. So I'm going to hit cancel. The one that I want is on the bottom here. And if I just hold my cursor over it, it says insert scatter or bubble chart. We want the scatter plot. We want just a bunch of dots. So I'm going to click on that. I want this very first one that just looks like a bunch of dots. I'm going to click on that, and you can see here's our scatter plot. All right, so we've got years on the bottom. We've got the times along the left side here. And you can see that obviously there's definitely a negative correlation here. Our data is decreasing as the years increase. And it looks fairly linear. I would call this a linear negative correlation. The question is, again, what is the line for this? What is the line of best fit for this that might cut through the data? And we're going to find R to give us some evidence as to how strongly that line fits the data. Is it a strong linear pattern? Is it fairly strong? What does that look like? Okay, so we've got our scatter plot. I am going to just click on this open area here. When I click on this open area anywhere on the chart, it's going to bring up the chart tools. And we want to make sure we're in chart design. And off to the very, very left, it says Add Chart Element. And I'm just going to click on that, and it brings down a drop-down menu. And you can see that there's a whole bunch of different stuff we can do. And I'm not going to concern us with that. If you want, you can obviously find videos on how to do this, use this stuff. You can play around with it yourself and just investigate. If you go down towards the bottom, there is something called trend line, and that's what we want. Line of best fit, linear regression, least squares line, trend line, they all mean the same thing. There's a lot of different names that are often given to these, but we want the trend line. Now, you can see that there's actually different ways that we can actually do this. We could do a linear. If you think that your data is actually not linear, there's other options as well. There's exponential, there's quadratic, there's power, there's logarithmic, all sorts of different regressions that you can use that would best fit your data. But ours is, we're going to say ours is linear. Now, you notice that just highlighting linear, it already pops up a dotted line through my data, but this actually is not what I want to choose. I want to go all the way to the bottom and choose more trend line options. When I do that, off to the right, I get a menu. Now notice that it's defaulted to linear, but you could change that if you thought that yours was something different, your data was something different. But the reason I wanted this is because I also, down towards the bottom, I want to be able to display some stuff on the chart. So right now I see my line, and it makes for a really nice picture, but I don't know what the equation for the line is. I don't know the R value. Those are the things that I really actually want from all of this. So down at the bottom, I'm going to display the equation on the chart, and I'm going to display the R value. I want these bottom two options. So display equation on the chart and display the R value. And you'll notice now we've got this here. It's kind of small. So if you want to make it bigger, you can actually edit this. I can go to home and I can actually increase the size of this so it's easier to read, so on and so forth. You can move it around. And so there is my equation and my R squared. Notice it's R squared and not R, which means that we would need to take the square root of that number to get R. And I'm going to do that when I come back to the notes in a minute. But that's one way of finding the equation and the R value. If that was too fast, obviously just go back in the video and watch it again. But let me show you another method for doing this. Okay, so I'm going to kind of close some of this up here. I'll leave this here, it doesn't matter. The other way to do this is if you watch the last video in this series, the previous video, one of the things that we did was we added a data analysis option to our data tab. If you missed that video, if you haven't watched that video, I'm going to very, very quickly go through how we get this data analysis if you don't already have it. To get this, we have to go all the way over to File on the far upper left corner. We're going to click on File, go all the way to the bottom to Options. And when you click on Options, it's going to bring up this menu. And we want add-ins towards the bottom. So on this left-hand column of options, we want add-ins towards the bottom. And what you're looking for is Analysis Tool Pack. Now, mine is already up above because I've installed it. Yours will be down below somewhere. Notice there's an Analysis Tool Pack VBA. You don't want that one. You want just the Analysis Tool Pack. You would just click on it and then click OK, and that's going to add that data analysis to your tab. All right. So we've got this in our tab now. And what I can do is I can click, just simply click on this. We don't need to highlight anything or do anything like that. Just simply click on data analysis. And yours will probably come up to the top like this, but down towards the bottom is an option for regression. And that's what we're looking for. So we've done data analysis. We're looking for regression. Highlight that, hit OK. Now I was working with this earlier, so I've got some information pre-populated here. I'm gonna click some of this off. This is probably what your screen looks like if you've not done a regression before on in Excel. By the way, I should also mention that Google Sheets, you can do the same thing. So if you're not an Excel user, if you prefer Google Sheets, exact same process, okay? All right. What we're going to do is enter our data, but notice that the data is reversed from what we'd be used to. This is our Y followed by our X. So it's asking, first of all, what are the output or Y values? So I'm going to make sure I've got my cursor in that box. I'm going to highlight the winning times. And then my X range is the years. Okay. You could obviously just hand type that if you wanted to. I'm not going to really worry about really anything else. You can decide where you want to output it and things like that. We talked about that in the previous video. New worksheet is just going to put another tab in the bottom. That's perfect. But down towards the bottom, this is what I want. I want the line fit plots. It's all you need to worry about right now. Just click on line fit plots and click OK. And that's going to create this new window. And if I make this a little bit bigger, you can see that it gives us not quite as pretty of a picture as we did before when we just made a chart. But you can see here the blue dots are the actual values. That's our data. The orange dots represent the predicted values at those locations for those X values. Okay. If you were to draw a line through the orange, you would have your line of best fit or your least squares line. What we're concerned about is in all of this data, down towards the bottom here, and let me expand this out here so we can see this. Right here, I'm going to highlight this for us so we can really see this. You have this thing called coefficients, this column called coefficients, and you have intercept and X variable. All right. Think about the equation for a line. The equation for the line is y equals mx plus b, right? That's slope-intercept form for a line, if you remember that from algebra. M is our slope, b is our y-intercept. Go back to the chart. These are coefficients. Intercept is our y-intercept. That's our b value. That's 48.478. M is the slope. It's the coefficient of our x variable. So the coefficient of our x variable, or our slope, is the negative 0.0189, etc. Okay? So if you use this method, that's where you're looking to get the values that you need to write the equation of that line. Okay, let's head back to our notes and let's write some of this down. So our least squares regression line, our model here, was y equals, the y-intercept is 48.478 approximately, minus 0. The slope is negative, so we'll do minus 0.0189x. Okay, now a couple of things here. First of all, notice that, again, if you think back to your algebra days, you might remember, as I mentioned before, that this is how we'd often write the equation for a line in slope-intercept form. We'd write the mx, the slope, the x, and then we'd have our y-intercept. In statistics, we often reverse that, and we'll often write the y-intercept first, and then the slope with the x. And the reason for that, and it'll actually make a lot more sense in an example we do a little bit later, or something we talk about a little bit later, is that sometimes you may want to apply multiple variables. So where we looked at simply the year and the winning time, we saw a correlation, right? We saw that correlation that as the years increased, the winning time decreased. But maybe there's another factor or variable that we want to consider also to see if that also has a correlation to winning time. Maybe it's somehow we can apply a value to something about the shoes, maybe something about the quality or technology of the shoe, and call that a factor. How did that affect winning times? Track surface, whatever it might be, temperature during the Olympics, right? Is there something else that we could use as a variable? So the idea is then that if you write it in this form, the y-intercept is oftentimes a constant, and then we're just adding and subtracting slopes and variables as we add more factors or variables to this equation. The other thing is that oftentimes you'll see a hat, what we call a hat, or just an upside down V over the y. And what that tells us is that this is a predicted value. That when we use this equation to find a value for y, it's not the actual value, it's just a predicted value. Okay. So for example, if I wanted to predict, if there was an Olympics held in 1970, right, right here, if I wanted to predict the value of the winning time for that Olympics, I could plug 1970 into my equation, get the value, but that's not the actual value because there wasn't even an Olympics in 1970. But my equation is giving me a predicted value. What would it predict the winning time to be if the Olympics were held in 1970? Okay, so sometimes you'll see a hat over that just to remind us that it is a predicted value. But that's our least squares line. And the other thing then is the r value. So again, remember that what they gave us r squared was 0.655. Well, to solve for r, to get the r value, the correlation coefficient, we have to take the square root of both sides because that square root is going to cancel out the square. So r, when we take the square root of 0.655, is 0.809. So what that tells me is, again, that should be negative, sorry. Well, okay, so let's talk about this. R squared is positive because r squared will always be positive. Whenever you square a number, it's always going to be positive. So you have to be careful here. When we take the square root, you always get a positive, right? So, but our r value is not positive, right? Because our regression was negative. It was decreasing. So we're going to throw a negative in front of this. It's actually a negative 0.809. And what that tells me is that we have a strong negative correlation. Strong negative correlation. Okay. So just be careful of that. When you are using r squared to get r, you have to take the square root, but watch your positive negative based on what the actual data is telling you. All right. So that's how we find least squares, regression line, and correlation coefficient. We are going to go through one more example like this, just to get this method down, just to make sure we've got it. And so we're going to look at Apple iPhones sold in millions in the phone's first weekend after release. All right. So we've got from 2007 to 2015, we've got the units sold in millions for each of the iPhones that was issued in each of those years. All right, so we're going to find the regression line for this and the correlation coefficient. So again, let's go back to Excel. I've got this also pre-populated here. Now, we have 3 columns. We don't really care about the first column. The first column is just telling us what kind of phone. We just really care about these 2 columns right here. What year was it issued in and how many units were sold. Now, just for purposes of getting that regression line, getting that R value, again, I'm going to use what I think is the simpler method of just inserting a chart because I'm going to use the other method for our next example. So again, if you want to insert a chart and find the regression line this way, we're going to go to Insert. We find the scatter plot. We insert a scatter plot. All right. And then I'm going to actually make this a little bit smaller here, just so it kind of fits on the screen. And then in this case, we are going to, again, just when you click on this, you get the chart tools. We want to be in chart design, go over to add chart elements, trend line, and more trend line options. So again, you can pick down at the bottom, display the equation, display the R squared value. And you'll notice that it's here on our charts. And again, I'll blow that up a little bit. All right, so there is our data, okay? High R squared value, right? So in this case, coming back to the notes then, I'll just write this down. Whoops, this notes. We've got y hat equals. I always do the y hat. I encourage you to do the same, but it wouldn't be necessary to do. Negative 3222.6 was the y-intercept. And then actually it was, negative. And then the slope was positive in this case. Plus 1.605 was our slope, x. Okay. All right. Whoops. I'm sorry. I thought I actually went to there. Okay. So that's our equation. And then our R value, again, our R squared was 0.9138. So R squared was 0.9138. So when we take the square root of that, R is the square root of that, which is 0.956. Again, this is positive, right? As our years increase, our units sold are also increasing. And so this has, I would say this is a very strong positive correlation, very strong positive correlation. Okay, now, check, we're done, except that we're not. Did this one for a reason, because if we go back to Excel and we look at our plot, we had a very strong correlation. We had an R value of 0.956. That is really, really strong. But look at the data. We just fit a line to data that actually isn't linear. If you look at that data, it's actually curved. It's not linear, it's curved, right? You've got this almost exponential looking curve to this data. All right. Here is the problem with R. R can be very deceiving. So don't rely on R to determine whether or not you actually have a really good line of best fit. R is kind of almost like the third tier that we look at. And I'll talk about that more in a minute. But what you really want to do is start by looking at your scatter plot and just ask yourself, does my data actually look linear or not? If it looks linear, great. Put a line to it. But if it doesn't look linear, you don't want to put a line to it because it doesn't make sense. It's like the proverbial, you put a square peg in a round hole. you don't put a line to a curve, okay? So, all right, let's go back to our notes here then. So, if we were going to, that would be our information. But again, we wouldn't actually use this. I'm going to come back to this example in a bit and show another way that we can tell that a line was not appropriate to pick for that data. All right. But we're going to go to a third example because I'm going to use this example now to really get into residuals and talk about how we find residuals and what residuals tell us and that sort of thing. So what we have here is we have heights and top speeds of 9 roller coasters around the world. Now, again, there's a lot of information in this chart. Most of it is just kind of flavor text. The only thing we really care about are those rightmost columns, the height and the top speed. And again, we're going to start by just finding the least squares line and the correlation coefficient, just like we did for the others, okay? So let's go back into Excel. Again, I've got this pre-populated, and we are going to find that information. Now, this time, though, do I want to do this or do I want to do the other method? I think I'm going to use the other method for this one. I'm going to use the data analysis for this. Let me delete this table so I don't get this confused, the one that we did earlier. And I'm going to delete this out. We're going to go to roller coasters, and I'm going to go to data analysis, regression down towards the bottom. Now, again, when we do this, we probably have some data now that's entered, so make sure that you either delete that or just highlight it and overwrite it. Here now, our Y input is the top speed. That's our output. Our input is the height. And again, the only thing that I'm really worried about right now is the line. Actually, you know what? I'm going to do this. I'm going to do the residuals plot also. We're going to add this in right away. So let's do residuals plot. Let's do both of these and click OK. And what we have now is we've got two different things. I didn't mean to grab that. Let's grab this and bring this down here. Bring this up here. Now, if I'm going to do this kind of separately, let me start with this one. So you can see here, we could change the values here. I could click on this and I could change this instead of starting at 0, where maybe it makes more sense to start at about 250. I can change this to 250 and just hit enter. And that makes our graph look a little better. I can change the height too. I can click on here and I could change the minimum height. Maybe instead of starting at 0, I want to start at 80, and I could do that. So you can kind of play around with it to kind of fit it more to the window, get a little bit of a better graph. Look how linear that is. That is a very linear data plot, a scatter plot, I should say. Okay. And in fact, let's see, where are our values here? We've got, there's our data to find the line. And our R value is up here. Let me expand this out again. R squared is right here. Let me highlight that one for you. That second line down, that's our R squared. Look at that. I'm going to find the square root. In Excel, if you want to find the square root, just hit equals SQRT. That's going to do square root. I could type in that number, or I could just highlight. Just say, I want to take the square root of the number in that cell. Hit enter. Look at that, 0.988. That is really, really strong. That's a very, very strong correlation. 0.988, 0.989 if we round correctly. Yeah, that's a very strong correlation. You can see that in the data, right? If you just look at the scatter plot, it's very, very linear, okay? So that's our information. We've got that. We've got this information down here that we want to get the equation of the line. And so the other thing that I want to point out is the residual plot. And then I'm going to go back and do a few things with residual. But since we're here, let's just talk about the residual plot. And again, I'm going to change this just so we can see this, but I'm going to start this at 250 again. Okay, so when we look at a residual plot, what the residual plot tells us is, again, what is the residual for each value in our data? Okay, in other words, how far away is the actual from the predicted? Remember, residual is actual minus predicted. So you can kind of see here, let me close this out. You can see here, if you look at this very first data point, blue is the actual, orange is the predicted. Blue is above orange. Our actual is bigger than predicted, which means that our residual, actual minus predicted, is going to be positive. Come over to the chart here. this is the point that represents the residual for these 2 points, okay? This is how far away these points are. So in this case, the residual is about 2.5, and it's positive, meaning that our actual is above the regression line. If you go to the next few points, the next 4 points, actually, they're all below. The actual is all below the predicted. Come over here, you'll see that those points are below or negative. Okay, so you can kind of see that correlation then in the residual plot to the actual scatter plot. And one thing to be careful of is don't obviously misinterpret the residual plot as the scatter plot and line of best fit. They're not the same thing, but visually they appear to have kind of the same characteristics. Okay. The residual plot is a really nice way to determine whether or not you've picked the correct regression line. All right. And I'm going to talk more in just a minute about what we look for to decide whether or not the residual line is saying, yep, linear was a good choice, or nope, maybe not so much. All right. But let's go back to our notes again and let's kind of summarize some of this and get a little bit more into residuals. So we found that our line of best fit, our least squares regression line, was y hat equals, our y-intercept was 20.1567. The slope was 0.2382x. And our R value was, again, about 0.989, very strong. Okay. So again, this is a very strong positive correlation, very strong positive correlation. Okay, so obviously as the height increases, the top speed of that roller coaster also increases in a very linear fashion, which is interesting. Okay, let's talk about residuals. So again, residuals as an equation, residuals we find by taking actual minus predicted. So let's say, for example, that I want to find the residual. We'll just take the first one. We'll take this Fury 325, okay? The actual value is 95 for its top speed, okay? If I want to find the residual, I need to find the predicted value. So what would my line predict the top speed to be for a roller coaster with a height of 325 feet? So what I'm going to do is I'm going to use the equation that we just found, this y hat, and so for y equals 95 for that first one, I'm going to find y hat by just plugging 325 in for x, because x is the height of the roller coaster. So we're going to take this equation, and we're going to plug in 2382. We're going to plug in, let's try that again. What was the height? 325. When I plug in the height, right, again, this is the height, that is going to give me, that's going to give me the predicted top speed for this roller coaster. And what we would get is y hat equals 97.57, what would that be, miles per hour, I assume? Miles per hour. Yep, miles per hour. All right. So that would be the predicted. So this is our actual, and this is our predicted. Okay. So the residual in this case, again, is the actual 95. The actual 95 minus the predicted of 97.57. And that gives us negative 2.57. Okay. So that's how you find the residual. Okay. And again, if your residual is negative, it means that the actual is below. So this means that our actual is below the predicted. And of course, you can see that by the values themselves. But if you're just looking at the residual, you would know that the actual is below the predicted just by the fact that it's negative. Okay. All right. So that's all a residual is. A residual is just what is the distance between those 2 points, the actual and the predicted, and the positive or negative just kind of gives the relationship as to which is above which. Now let's talk a little bit more about the residual. First of all, one of the other reasons that the residual is important is the residual is actually used, as we talked about before, in finding the actual least squares regression line. So all the math that's being done behind the scenes to get this equation that we found is done by using residuals, right? That's part of the process. And so we need residuals to find that line. But then it also gives us, again, it gives us that residual plot. And I want to talk more about the residual plot for a minute, because the residual plot is important in helping us to determine whether or not we've chosen the correct, in this case, linear, chosen linear correctly versus maybe it should have been exponential, or maybe it should have been quadratic or something else, okay? So when we look at the residual plots, if we want to know whether or not it was a good fit, what we are looking for is we want a random, fairly even scatter, of points above and below y equals 0. Above and below y equals 0. Okay. I'll go back to the residual plot in a minute and just kind of show this again, but you want those points to just kind of look real random and scattered above and below the line. All right. The second thing is you don't want to see any outliers. Okay. You don't want to see a point that's really far above or really far below the other points. You want the points to be fairly consistently distanced from y equals 0. Okay. So no outliers, no curved pattern. Usually a curved pattern is going to be like a U shape. So we don't want to see a U shape in our data, either right side up or upside down. And no, I guess what I'm going to call it kind of like a sideways pine tree. So I'll put it down here. No, like sideways pine tree. I know that's a really odd description. But what I mean by that is this. What we don't want is something where your scatter plot looks like this, where it starts out really narrow and then gets wider and wider as you go further and further away, or opposite, where it'd be really, really wide and then narrow down as you go further on. Okay. So let me go back to Excel for a minute. And let me show you the residual plot again. So if we look at this residual plot, you'll notice that there's not really any pattern here. Like the points are just kind of above, below. Now we do have kind of a grouping of points below, but that's not real concerning. As far as distance, yeah, not too bad, between about -3 and +4. It's kind of just it's a residual plot. All right. But let me go to the iPhones. Okay. And let me do the data analysis for the iPhones and show you the residual plot for that one. And so we're going to go okay. And actually, we need to change our data here. So this one is going to be, this is the millions sold, and this is the year. All right, we're going to click OK. All right, so notice the residual plot on this one. And this is what I'm talking about. This has a very obvious U-shaped pattern to it, this curved pattern, where you have points above, you've got points below, and then you've got points above. Now, again, it could go the other way. It could go up, down like this, and that would also be considered a U-shaped curved pattern. This tells me that a line is not a good fit for this data. If we look at the actual plot itself, the scatter plot, which is always the best place to look, if you can see the raw data in its scatter plot form, that's always the best. Look at, again, the curve of that. And what's happening is when you try to draw a line through a curve, that line is going to intersect the curve twice. In this case, it starts below the curve, it intersects it, goes above the curve, intersects it, and drops back below. And so what you're seeing is you've got points, actual points above the line. Those are going to result in points above y equals 0 on your residual plot. Then you've got points below, and then you're back to points above. And that's what's creating this U-shaped pattern in our residual plot. Points above, points below, and then back to points above as that line cuts through that curve. All right. So That's the residual plot, and that helps us again to just kind of figure out whether or not a linear regression is an appropriate choice for our data. So as we think about then how do we what's kind of the progression of determining that, we always start with the plot itself. If you can look at the scatter plot and just see the data for what it is, that's always your best first choice. Second choice is the residual plot. Then, and only then after you've looked at those two, do you look at R and possibly what's called the standard deviation of residuals, which we haven't talked about. But that would R and S would be kind of the two things that you would look at also. Okay. All right. So with that, we are going to transition just a little bit, and we are going to now talk about what is called the coefficient of determination, or R squared. So let me start with this. Let's talk about the difference between R and R squared. And I'm going to just kind of come out with what R squared does, and then we'll look at an example to see kind of the how or why it works. So R, let's start with R. R is really explaining how well does the line fit the data. So R explains how well the line, I'll say it this way, the least squares regression line, right? The least squares regression line fits the data. So in other words, again, the larger the R, right? The bigger that R value, the closer to 1 or -1, the more linear our data is. The closer to 0, the less correlation there is. The points are scattered all over, and we don't know if our data is increasing or decreasing. We don't see a correlation between the two variables. Okay, so R is about fit. R squared. So R squared. I'm gonna say it this way. R squared seeks to answer the question. How do I say this? How much does the LSR, let's say it this way, how much does the LSRL account for or explain the variations? How much does the LSRL account for or explain the variation in Y, whatever Y happens to be your output, using X? Okay, so I know that sounds a little bit nebulous right now. Let me try to write this so it actually is legible. I know this is a little bit nebulous right now, but what it's really doing is it's saying if I look at, well, let's just do an example. All right, let's take a car lot. Let's suppose I'm the owner of a car lot. I sell used cars. I don't do new cars. I just sell used cars. All right, and to be more specific, I only sell Toyota Camrys. All right, so I sell Toyota Camrys, and we're going to look at the value of used Toyota Camrys. All right, so we've got used Toyota Camrys, not Camrys. All right, so let's say that I have decided, I own hundreds of used vehicles. It's a big car lot. And I have decided that based on the values of the cars, the average value of a car on my lot is $15,000. Okay, so I am going to just draw a horizontal line. So that's the average value of a car, $15,000 on my lot. All right. If I was crazy, I would just say, you know what, every car on my lot is $15,000. It doesn't matter what the car is. You give me $15,000, you drive away, and you'd say I'm crazy because we all know that not every used Toyota Camry is worth $15,000. Some of them are only worth $2,000. Some of them are worth $25,000. So to say that that I'm going to sell them all for $15,000, we know doesn't make sense. So how do I differentiate values among those used Toyota Camrys? What are the factors or the variables that contribute to the different values of those cars. So we might say things like, well, miles, how many miles the car has, that's going to affect its value. The more miles it has, the less it's worth. Or we might say that the age of the car impacts the value. The older the car, the less it's worth. Maybe the options that are on the car, what kind of features does it have? It could be maybe it's the color. Maybe red Toyota Camrys are not real popular. People don't really want them. They're worth less than, say, a white, black, or gray, something that's a little more neutral in color. So there are a variety of variables or factors that impact the value of a used Toyota Camry. Okay, so let's just pick, for example, miles. All right, so on our y-axis, we have the value of the car, right? This is in dollars. We've got the value of our used Camry, and we're going to say right now that the average is $15,000. And I am going to look at the value of the car in terms of miles. Okay, so I look at very low mileage cars, and low mileage cars, they're going to be worth more than $15,000. But at some point, you get enough miles on that Toyota Camry, and they're going to be worth less than $15,000, right? And let's just assume we have a nice, just linear pattern like this. Okay, I didn't necessarily mean it to be quite so perfectly in that clump or cluster, but that's actually fine. Okay, so I'm going to find a least squares regression line to fit this data. Okay, so I find a least squares regression line that, again, cuts right down the middle of all of this data. And I could use that now to predict the value of a used Toyota Camry based on number of miles. Okay. I also find an R value, and an R squared value, excuse me. Let's just suppose that R squared is 0.58. So now let's go a little higher. Let's go 0.72. All right, let's suppose that R squared is 0.72. What that means is that when I look at the price of the car, the value of the car, only looking at miles, I'm not looking at the age of the car, I'm not looking at the color of the car, the options it has, nothing else. I'm just looking at miles. Instead of all of my cars being worth $15,000, I've differentiated the prices now. I've differentiated, again, some cars to be more expensive if they're low mileage, and some cars to be less expensive if they're high mileage, right? So I've differentiated, I've varied the value of those cars based on miles. To the extent that my model predicts the value of a car using miles is given by the R squared. Okay, so in this case, how I might interpret this is I might say, for example, if R squared is 0.72, I might say 72% of the variation, 72% of the variation in used Toyota Camry prices, is explained by or accounted for. You can kind of use whatever wording you want for. I tend to use it as accounted for, but I think explained by is a little bit easier to understand. Is explained by the LSRL, least squares regression line, using miles driven. Okay. In other words, the value of the car in relation to how many miles it has is a pretty good estimate. 72% of that variation in price is accounted for or explained by miles driven. If I did the same thing, but I changed miles to age of the car, okay, and let me just show it. So let's do this again. This time, here's my average, right? Here's 15,000. Okay, but this time I'm going to look at the age of the car versus the value of the car. Again, newer cars we'd expect to be worth more. Older cars we'd expect to be worth less. So maybe now my newer car is worth, looks like this, right? Maybe my data looks like that. Now notice it's a little more spread out, right? That was a nice, packed data set.
my data is a little more spread out, but I can still see a correlation. I can still see a general negative pattern. I can still see that it's fairly linear. And if draw my least squares regression line, I can get a model that would predict the price based on age. But it's not as tight, right? Age didn't do quite as good of a job of predicting the value of a car as miles driven. So in this case, maybe age gives us an R squared value of 0.20. Okay. Maybe age only actually accounts for 20% of the variation in price. Okay. So that's as we look at different factors, different variables, you're going to have different impacts on that variation. If I looked at color, I'd probably have a really, really small R squared value. Maybe color only accounts for 1 or 2% of the value of the car. And so that's what R squared does. It just simply takes a variable and says, how much can we explain the difference in prices in this case based on that particular factor or variable? That's what coefficient of determination does. All right, I hope that was helpful. I hope that kind of explains that for you. We are going to move on and finish now with some stuff from chapter 13. So that was all chapter 4. And now we're going to head into chapter 13. And I know what you're thinking. You're thinking we're about an hour into this lesson, and we're now just hitting chapter 13. And don't worry, this is very, very short. It's big, it's important, but the concepts are pretty straightforward and going to be pretty short to explain and do. In previous lessons, we looked at how to construct a confidence interval, and we looked at how to do hypotheses tests or significance tests. We are going to do both of those for slopes of a regression line. Okay, and I'll explain what that means exactly as we do this. But if you remember what a confidence interval is, a confidence interval, we'll start with that one, is creating a range of values that we believe contains or captures some actual value about the population. So again, to just refresh, or if you didn't watch that previous lesson, if I wanted to, let's take our Toyota Camry example. Let's say I wanted to predict the actual average price of all Toyota Camrys in the world. So I take a sample of Toyota Camrys, and I use that sample of used Toyota Camrys. I look at their values, and I use those values to create a confidence interval. And when I create that confidence interval, it's saying that I believe that inside of that interval is the actual average price of all Toyota Camrys in the world. Okay, so we're going to do this for slope. All right, so let's start by just defining again the least squares regression line. So we're going to define it this way. We're going to say that a least squares regression line, remember we kind of think you probably learned y equals mx plus b. We're going to do something similar, but we're going to use b0 and b1. So I'm going to say that a least squares regression line has this form. b0 is my y-intercept. b1 is my slope. Okay. Now, there are some other pieces of information that we need to know in order to do this. And these are, again, things that you could find if you did Excel, do the data analysis. You're going to find these values in places like that, or a lot of times they're just in academic problems, textbook problems, things like that. They're often just given to you as values. They're not necessarily things that you would be expected to find on your own. So the first one is what we call S sub E, or the standard deviation of residuals. So this is standard deviation of residuals. And again, this is a value that would likely be given to you, or you could find from some kind of software output. And just like normal standard deviation, if you know what normal standard deviation is, or have watched that video, standard deviation tells us the typical distance of our data from the mean. Okay. Similarly, the standard deviation of residuals is the typical distance. It's the typical distance of the actual values from the predicted values. So again, if you think about those residuals, and you think about the lengths of those residuals, how far the actual is from the line, standard deviation of the residuals tells us typically how far away the actual data points are from the regression line in a vertical sense. Okay. Then we also have something called S sub B, and that is the standard error of the slope. So it's the standard error of the slope, or B1. Okay, again, B1 just being slope. Basically, the S sub E, the standard deviation of the residuals, is used to find the S sub B. Okay. Now, again, you would typically be given this information in some kind of textbook problem, or you'd find it in Excel or whatever. All right. Confidence interval then. Let's talk about that. So now we've got these couple of variables defined. Let's talk about the confidence interval for slope. So confidence interval for slope. And the way that we find confidence interval for slope is, remember that a confidence interval is a point estimate. It's a mean, it's a proportion, it's some kind of value, plus or that's from our sample. It's from our sample specifically, plus or minus margin of error. Okay, so it's some kind of value from our sample, plus or minus margin of error. So in this case, our point estimate is going to be B1. It's going to be our slope of our regression line, right? Up here, we defined it as our slope of our regression line. Plus or minus, we're going to use T. We've used T before, okay? Times S sub B, all right? Now, we find T, if you remember, using a table, but in that table, we don't use, we need a DF. Normally we do DF is sample size minus 1, but because we're dealing with two variables now, we find DF by doing n minus 2, okay? And again, that's because the predicted value involves two parameters, not one. So every time you add a parameter or a variable, you're subtracting another value from your DF, okay? So we're going to do DF equals n minus 2. All right, so this is how we find confidence interval for a slope. That's our formula, all right? Pretty straightforward, because we're pretty much going to be given a lot of this for us. Or again, like I said, we're going to get it from the Excel, and I'm going to show you that right now. So we're going to construct two confidence intervals for slope using the roller coaster data that we did before. We're going to do one confidence interval at 90% and one confidence interval at 95%. Okay. Now, let's go back to our Excel sheet then. And this was our data that we had gotten. So let me just kind of minimize this so we can see this. Okay. So right now, we're looking for a couple of things here. Let me get rid of this also. Just try to create as little confusion as possible. We need to find B1, and we need to find T, and we need to find S sub B. Okay. So how do we find all of this so we can actually get our values? Well, so remember that B1 is our slope. So this is our slope right here. Okay, so that's one thing that we need. That's our B1, that's slope. Another thing we need is our S sub B, that's our standard error for the slope. Well, standard error for the slope, here's standard error here. Here's the title standard error. For our slope, that's going to be the number right next to it. So that's so this is, I'll kind of type this in. This is our slope, and this is our S sub B. Okay, this is our standard error for the slope. All right, and then T, we would have to go to the table to get T, and just remember that for that, what you're doing is you're basically going down to DF, and you're going to go across until you find the percentage that we're looking for. In this case, we'll start with the 95%, and you get that T value. And in this case, I'll give that when we get back to our notes. All right. But this is where you find those two values in the charts. Slope and standard error is right next to it. Okay, let's go back and let's go to our notes here.
Okay, so to find our confidence interval, again, we're going to start with the 95% first, and I'll give you a very obvious reason for that in a minute. But we're going to take our B1, that was our slope. So our slope was 0.2382 plus or minus. If you go to the chart, just use the T-table charts, we get 1.943. Okay, again, in this case, DF. We had 8 roller coasters, I believe was the total number of roller coasters we had. So our DF is going to be 6. And then times the standard error of 0.0148. Okay. So again, this is our B1. This is T star, the T value from the chart. And this is going to be our S sub B. All right. And what that gives us is a confidence interval of 0.202 to 0.274. All right. What that means is that if I were to do, so again, think about what we did here. To get the least squares regression line, you would collect a bunch of sample data, you'd plot it, and you'd calculate the least squares regression line using some kind of technology, right? That least squares regression line has a slope. If I were to sample another 8 roller coasters and do this again, I would get a different least squares regression line because it's 8 different roller coasters. And if I did this again, I'd get a different least squares regression line. Every time I take a new sample of roller coasters, my least squares regression line is going to change. However, if in fact height of a roller coaster does predict top speed as much as we believe it does, I should find that the slopes should be fairly close to each other. And that the actual slope, if I could take all of the roller coasters and do the, find the fit, the least squares regression line for all roller coasters, the slope that I would get from that regression line, I believe, is somewhere between 0.202 and 0.274. I'm 95% confident that for all roller coasters in the world, if I took all those top speeds and heights, that the slope of that regression line for that data would be somewhere between those two values. Okay, let me write that out. I would say something like I am 95% confident, that's our confidence level. I am 95% confident that the slope of the population LSRL, right? So this is the least squares regression line that I would find if I had every single height and top speed of every single roller coaster in the world. So this is the population LSRL for height and fastest speed. Those are the two variables that we're comparing here. Is between 0.202 and 0.274. That would be how we would interpret that, okay? Now, why did I want to start with the 95%? Our values that we found using this method were 0.202 to 0.274. You might have noticed this in the data before if you're paying close attention, but if we go back to Excel, here's our right, this was our slope and our standard error that we found. But if you keep going across, notice that there is this lower upper 95%. And look at those numbers. If you round them, 0.202, 0.274. Those two numbers right there, I'm going to put that in orange here. Those two numbers are the ends of our confidence interval. So when you do this in Excel, you don't even have to do the work of that formula. Excel just automatically gives that to you. Now, it gives it to us twice, which is a little odd, but let's talk about that. Let's go back to roller coasters, and I'm going to redo the data analysis. That's how we got that table in the first place. So I'm in my roller coasters. I'm going to do data analysis,
and we're going to do regression. And again, I've got to change my data because this was for a different problem. Y is our top speed. This is our height. And notice that right under that, there's the ability to change your confidence level. I'm going to change my confidence level to 90% because that's the other problem we wanted to do for this. We wanted to do this for 90% and 95%. I'm going to change this to 90%. I'm going to get rid of this residual plots and stuff. I don't really need that at all. In fact, even the line fit plots, I don't need any plots. I need data. I'm going to click OK. And I get a new sheet now because, again, it just calculates a new sheet every time you do this. But notice now, let me expand this out so we can see this. Notice now we've got the lower 95%, upper 95%, but now we've got a lower 90 and upper 90%. So here's our range for a 95% confidence interval. Here's our range for a 90% confidence interval. So Excel will just do this automatically for you. You don't even have to calculate a thing. Just put in your data, do data analysis, and you've got your confidence interval. All right. So that's how to do a confidence interval. Now, of course, you could always do it by hand, and there's nothing wrong with that. This is just, again, the method for it. You would just need the table to find the 1.943 and get your information from, whatever sources you're using. All right, let's move on and let's finish now with doing a hypothesis test for slope. And I'm going to just dive right into this and use the information we have to kind of show you how to set this up and do this. And we will finish with this. So we want to test the hypothesis where the null is that the slope is 0. And the alternative is that the slope is greater than 1 using an alpha equals 0.05. So using a significance level of 5%. Can we conclude that the height of a roller coaster is useful in predicting the fastest speed of a roller coaster? Okay, let me explain this. That's kind of a lot here. Let me kind of rewrite this in the form that we are familiar with. So our null is that the population slope is 0. What does that mean? That means that there is basically no correlation between height and fastest speed. Doesn't matter if you were to graph fastest speed, the impact of fastest speed based on the height of the roller coaster, you would get a horizontal line. No matter what the height is, the top speed is always the same. That's what that's saying. Now, we believe, of course, that it's not that. That if I increase the height, I'm also going to increase the speed. That the slope is positive. Okay, so let me just kind of draw that out. So the first one is saying, here's my height, here's my speed, right? H null is saying there is no difference. Pick any height you want, the speed never changes. The alternative is saying not really true. As height increases, your speed also increases. You're going to have a positive slope, okay? All right, so how do we actually run this test? Well, again, we're going to find a test statistic. We're going to find T, okay? But T is found by taking B1 divided by S sub B, okay? So those same values that we found earlier, here's S sub B, here's B1, those same values are what we use to find T itself, okay? So I'm going to take 0.2382, that's the slope. I'm going to divide that by the standard error of the slope, 0.0148. And that gives me a t value of 16.09. Now notice that that's not the same as this t, right? This is a different t. This is a t star that we got from the chart. This is just a t score. This is like z or t. This is different, all right? Again, we need a DF. Our DF, we had 8 roller coasters, minus 2 gives us a DF of 6. So I'm going to take us to the table this time. We've got a DF of 6. We've got a T value of 16.09. And so this is the table that we've been talking about. So again, this is where if you're finding the critical value for the interval, you would go down to the bottom, find your percent, and then come up to your DF to get the number. So remember that our number in the interval was 1.93 or 1.943. That was this number right here. That's because we did a 90% confidence interval with a DF of 6. Okay, so for this one now, we're looking for, again, our DF is 6, and we're going across now the row until we find the 16.09. Well, if you notice, as we go across the row, we go. The highest this goes is about 6, right? This is about as high as it goes. So we're way off the table. And if you look at the top row again are the probabilities. In this case, our probabilities get smaller and smaller and smaller and smaller. This is basically going to 0. What that tells me is that from this, my p-value is approximately 0. I get that from the table. And because of that, because it's less than 0.05, we are going to reject the null. Okay, so let's write that out. So we reject the null. Basically, I'm just going to say because we have convincing evidence, or there is convincing evidence, however you'd like to say that, we have convincing evidence. In this case, because we're saying that the slope is greater than 0, we're saying that correlation is positive, right? So again, as height increases, top speed also increases. So I'm going to say exactly that. So we have convincing evidence that how do I say this? That I'll say that the taller the roller coaster, the faster the top speed. And that is because the null specifically, because we concluded from the alternative that the slope is greater than 0. Right? So because of that, we've got that positive correlation that the taller the roller coaster, the faster the top speed. Okay, now that's the problem. Okay, so again, you set up your hypotheses. Notice there's no checks here. First of all, you don't do any checks for this. You just jump right in. So we're going to do our hypotheses. We find t. We compare it. We use that to get p from the table. Compare it to alpha. If it's less than, we reject the null. If it's greater than, we fail to reject, and then we write out our conclusion. Pretty straightforward. Again, if you watched the video on hypotheses tests earlier, this should make a lot of sense. Now, let me show an even easier way. We're going to go back into Excel. Remember, our p-value is approximately 0. We're going to go back to Excel. And in Excel, this is our summary output for the roller coaster problem. This is where we had our confidence interval data and all of that. And notice here, there is a p-value. I'm going to highlight that. There's our p-value. And we want the p-value for the variable. So make sure you grab the lower one, not the upper one. We want this lower number. And if you're not familiar with that notation, with that E is just scientific notation. So this is saying 3.68817 times 10 to the negative 6th. All right. So I'm gonna write that out. I don't actually have this written in my notes. I'm gonna write this out and then bring you back to my notes. So it's 3.6888 or 8817 times 10 to the negative 6th. All right. So let me take you back to the notes and let's talk about this number. So if you remember scientific notation, if you know scientific notation, that times 10 to the negative 6 means that we would take our decimal point, and move it left 6 places. If it was positive, we'd move it right 6 places. So we're going to basically take 3.68817. We're going to take that decimal place and go 1, 2, 3, 4, 5, 6. And for every one of those, we have a 0. Okay, so again, 1, 2, 3, 4, 5, 6. So this is basically 0.000003. In other words, it's approximately 0, right? That's our p-value. So Excel gives you the p-value. So you don't even have to go through the process of finding t, going to the table. You could do a data analysis in Excel and just grab the p-value right out of here and then make your conclusion based on how that p-value compares to the alpha or significance level. So that is how we do a significance test or a hypothesis test in or for a slope. And that brings us to the end of this lesson. That brings us to the end of this series. I hope that you have found this to be very beneficial. And if you haven't watched the previous videos, I certainly encourage you to go back and do that. And again, I just want to thank those of you who have gone through the entire series, watched all the videos. Thank you for doing that, and take care.